Black holes are the most extreme objects the universe has ever created. They are regions of space where gravity becomes so strong that nothing can escape, not even light. A black hole is not a hole in the way we imagine holes on Earth. It is not an empty tunnel. It is not a crack in space. It is a place where matter has collapsed into something so dense, so compact, and so heavy that the rules of ordinary physics stop working. For a long time, black holes were not considered real. They sounded like strange mathematical mistakes inside Einstein's equations. Even Einstein himself believed nature would never allow something so extreme to form. But the universe does not care about our comfort or our assumptions. If physics allows something, the universe will eventually create it. And it created black holes everywhere. They sit in galaxies, in clusters, and even in places where no stars remain. Right now, there may be millions of black holes quietly drifting through the Milky Way. A black hole begins with collapse. A massive star burns through its fuel until nothing is left to push outward. Gravity wins. The star shrinks. Then it collapses into a point so dense it has no size. This point is called a singularity. Around this singularity forms an invisible boundary called the event horizon. This is the surface of no return. Once anything crosses that boundary, it cannot escape. Not matter, not light, not information, not even time in the way we normally experience it. The idea that something could trap light completely was unthinkable centuries ago. Light was seen as pure, untouchable, beyond gravity's reach. But gravity does not care. Gravity bends space, and if space bends enough, even light curves into it. A black hole is not a force pulling on light. It is space-time itself collapsing inward, forming a region where all paths lead down. Think about that carefully. Outside a black hole, you can move in many directions, up, down, left, right. Inside the event horizon, every direction becomes toward the singularity. Not because you're being sucked in, but because space-time is shaped in a way that gives you no other path. Even time begins to behave strangely. Far from a black hole, 1 second is 1 second. But near the event horizon, time slows. A clock near a black hole ticks slower than a clock far away. This is not an illusion. It is a real change in the flow of time caused by extreme gravity. Now imagine watching someone fall into a black hole. To you, the observer far away, they appear to slow down. Their movements become sluggish. Their image grows dimmer. The light coming from them shifts to red. They freeze on the edge of the event horizon, fading slowly until they vanish. But they never appear to fall in completely. To the person falling, everything feels normal. They drift. They fall. They pass the event horizon without noticing anything special. The crossing is silent. There is no boundary wall, no sudden shift, no sensation at all. But once inside, escape becomes impossible. Gravity stretches their body. Their feet feel a much stronger pull than their head. Their body begins to elongate like soft dough. This effect has a simple name: spaghettification. Near smaller black holes, this stretching becomes violent. It tears objects apart atom by atom. But near supermassive black holes, the event horizon is large and gentle. You could cross it without being ripped apart immediately. Inside, space-time narrows. All directions lead toward the singularity. The fall becomes unavoidable. No force, no engine, no resistance can stop it. The singularity is not a place you can visit or observe. It is a region where density becomes infinite, curvature becomes infinite, and physics as we know it stops providing answers. Black holes challenge everything we think we understand. They show us where our theories fail. They show us where the known universe ends, and deeper mysteries begin. Every black hole comes with only 3 properties: mass, spin, and electric charge. That is all. It does not matter what originally fell in: a star, a planet, a cloud of gas. All the details are erased. The black hole keeps only the total mass, the total rotation, and the total charge. Nothing else survives. This is one of the most disturbing features of black holes. They erase information about matter. Physics does not like erasing information. Laws of nature demand that information is never lost. And yet, black holes seem to break that rule. This conflict produces one of the greatest mysteries in science, the black hole information paradox. But that puzzle comes later in this series. Before we reach it, we must understand how black holes form, how they behave, and how they shape the universe. Because black holes are not just destroyers, they are also builders. They shape galaxies, they guide star formation, they anchor the centers of cosmic structures. At the center of the Milky Way sits a giant black hole called Sagittarius A. It has a mass of about 4 million suns. Every star you see at night orbits this dark center. If that black hole did not exist, the Milky Way would not hold its current structure. The galaxy you call home is organized around an invisible object that bends spacetime so deeply that nothing can escape it. Black holes exist at many scales. The smallest ones are only a few times the mass of the Sun. They come from the death of massive stars. The largest ones, supermassive black holes, contain millions or even billions of solar masses. These giants existed very early in the universe, even before many galaxies fully formed. How they grew so fast is still a mystery. They might have formed from the collapse of enormous gas clouds, or from the merger of smaller black holes over billions of years. Between these two sizes may lie another category, intermediate black holes. These are harder to detect, but may exist in star clusters and dense regions of galaxies. Scientists suspect that intermediate black holes act as seeds that grow into supermassive ones, though the process is still unclear. What makes black holes powerful is not just their gravity, it is their influence on everything around them. When matter falls toward a black hole, it forms an accretion disk. Gas spirals inward, heating to millions of degrees. Light erupts from this disk with incredible intensity. Some black holes even launch jets, beams of energy that shoot out at near light speed for thousands or even millions of light years. These jets can shut down star formation in galaxies. They can heat massive clouds of gas. They can reshape entire cosmic environments. A single black hole can control the fate of billions of stars. It is ironic. The darkest objects in the universe create some of the brightest phenomena. They hide all light inside their event horizons and yet produce some of the most violent and luminous events known to science. The universe is full of contradictions like this. Black holes are the center of many of them. The term black hole itself is relatively new. It was coined in the 1960s. Before that, scientists called them frozen stars or gravitationally collapsed objects. Today the term is familiar, but the reality is still as mysterious as when it was first imagined. The gravity near a black hole is so intense that it bends the path of light. This bending creates gravitational lenses, distorted images of stars and galaxies behind the black hole. We have even photographed a black hole's shadow using the Event Horizon Telescope. That black hole sits in the galaxy M87 and contains billions of solar masses. Its shadow is a perfect example of spacetime collapsing inward. But the shadow is not the black hole. It is the region where light cannot escape. The actual singularity is hidden behind the event horizon, unreachable and unseeable. Black holes show us where our understanding stops. They show us the limits of Einstein's relativity. They show us the conflicts between gravity and quantum mechanics. They show us that the universe is not finished teaching us. Every time we study a black hole, we discover something stranger. They merge, they vibrate space-time, they produce gravitational waves that ring across the universe. They evaporate slowly over trillions of years through Hawking radiation. They are not dead, they are active, they are evolving. Black holes are the engines that rewrite reality. They change matter into energy. They twist space. They stretch time. They erase information. They hold the secrets of a deeper theory of physics that we have not yet found. And to understand them, we must go deeper. We must understand how stars die. We must understand how collapse begins. We must understand why gravity becomes unstoppable. That is where the next part begins. Black holes begin with stars, not the small stars that burn gently for trillions of years, but the massive, unstable stars that live fast and die violently. To understand black holes, you must first understand how these giant stars are born, live, and collapse. Because a black hole is not created out of nothing. It is the final stage of a star losing the fight against its own gravity. A star is a balance. Gravity tries to pull everything inward. Heat from nuclear fusion pushes outward. As long as a star has fuel, the outward pressure balances gravity. The star glows, it shines, it lives. This balance is delicate and temporary, because fuel does not last forever. A star begins as a cloud of gas and dust. A small disturbance, maybe the shockwave from a nearby supernova, causes the cloud to collapse. Gravity pulls the cloud inward. As the gas compresses, it heats up. Eventually the temperature becomes so high that hydrogen atoms begin to fuse into helium. This fusion releases energy. The star ignites. Every star in the sky went through this process. Small stars burn their fuel slowly. They live calm, stable lives. These stars end as white dwarfs, not black holes. Medium stars, like our Sun, burn faster. They swell into red giants and eventually shed their outer layers. They also end as white dwarfs. But the giant stars, stars 10, 20, even 50 times the mass of our Sun, live short, violent lives. They burn fiercely. They shine brighter than thousands of suns. And because they burn so fast, they die young. A massive star's core becomes hotter and denser over time. It fuses hydrogen into helium, then helium into carbon, then carbon into heavier elements. Each stage produces less energy. Each stage brings the star closer to collapse. When the core tries to fuse iron, everything stops. Fusion no longer produces energy. It consumes energy. The balance breaks, gravity wins. The core collapses in less than a second. The outer layers fall inward. The star rebounds violently. A supernova explodes. For a brief moment, the light from that explosion can outshine an entire galaxy. If the collapsing core is massive enough, collapse does not stop at any stable point. The core collapses into a black hole. This is the birth of the simplest, most powerful object in the universe. Now think about what this collapse actually means. A star that once glowed for millions of years is crushed into an object only a few kilometers wide. A mass greater than the Sun is compressed into a sphere smaller than a city. In that moment, matter stops behaving like matter. Atoms break, nuclei break, even particles may break. Nothing is strong enough to resist that collapse. Not light, not pressure, not atomic forces. This is why the center becomes a singularity. Outside the singularity forms the event horizon, an invisible surface that marks the boundary between escape and no escape. The star's identity is gone. Its entire lifetime, its fusion, its light, its planets, its history is erased and replaced with a black hole defined only by mass and spin. But not all black holes form from a single collapsing star. Sometimes, two dead stars collide, two neutron stars spiraling inward after millions of years of orbiting each other. Their merger creates a burst of light, gravitational waves, and a black hole. Sometimes, large clusters of stars create black holes in the crowded chaos of their cores. Sometimes giant gas clouds fall inward and collapse directly into massive black holes without forming stars at all. The universe has many paths to create a black hole. Some black holes are small, some are enormous, some are ancient, some are forming right now. If you look at the Milky Way, black holes are scattered everywhere. Tens of millions hide silently between the stars. They do not glow, they do not shine. They cannot be seen directly. They drift, dark and quiet. Only when they interact with nearby matter do we notice them. A black hole that feeds is bright. A black hole that drifts alone is invisible. Now think about the journey of matter that falls toward a black hole. Gas and dust spiral inward. As matter compresses, it heats to millions of degrees. It glows with X-rays. It forms a disk of violent motion. This accretion disk is often brighter than the entire galaxy around it. The black hole itself remains black, but the space near it shines intensely. This is another contradiction. A black hole is the darkest place in the universe, yet it can be surrounded by some of the brightest light ever produced. Some black holes are quiet, some are violent, some are newborn, some are billions of years old, but all of them share one truth. They are the end of a star's life. Now think about stars again. Stars create everything. The carbon in your body, the oxygen you breathe, the calcium in your bones, these were forged inside stars. When stars explode, they scatter those elements into space. New stars form, new planets form, life eventually forms. Black holes are not destroyers of matter, they are stages in recycling. The universe grows through collapse. It evolves through death. It builds through destruction. This is not poetic language. This is physics. Stars die so new stars can form. Supernovae enrich galaxies. Black holes stir matter, heat gas, and influence the birth of new generations of stars. Black holes emerge from star death, and yet they help shape the future of galaxies. Now, think about the timeline of the universe. The first stars were enormous, hundreds of times the mass of our sun. They burned quickly. They collapsed violently. They created the first black holes. Those black holes merged. They grew. They seeded the centers of galaxies. They shaped the cosmic web. The Milky Way itself may not have formed the way it did without black holes guiding matter through gravitational influence. The early universe was chaotic. Gravity had to gather matter into larger structures. Black holes acted as anchors. Every galaxy we know, large or small, has a black hole at its center. Our Sun orbits Sagittarius 8, the supermassive black hole at the heart of the Milky Way. Without it, our galaxy would not have the structure we see today. Our spiral arms, our rotation, our density, our star formation history, all of it is tied to that central black hole. Black holes are not accidents, they're essential components of cosmic architecture. Now consider the emotional scale of this. A star that shined for millions of years ends its life in silence. It collapses into a point of infinite density. It becomes something completely different from anything we experience in everyday life. The star's identity is gone, but its influence continues. What was once a source of light becomes a shape that bends space-time. The universe does not throw anything away. It transforms everything. The death of a star gives birth to a black hole. The black hole shapes galaxies. The galaxies shape star systems. Star systems create planets. Planets create life. Life creates awareness. Awareness tries to understand where it came from. And so you sit here, thinking about the death of stars and the birth of black holes, using atoms forged inside ancient stars to contemplate the universe that built them. This is the quiet connection between you and every black hole in the sky. You exist because stars lived. You exist because stars died. You exist because collapse created new beginnings. Black holes are not the end of the story. They are part of the story structure. Now the next question becomes natural. If black holes come from collapse, what happens at the boundary of the collapse? What exactly is the event horizon? And why does crossing it erase the universe behind you? That is where the next part takes us. Black holes are often described as places where nothing can escape, but that statement alone does not explain why a black hole is so different from anything else in the universe. To understand the true nature of a black hole, you must understand the event horizon. This invisible surface is not a physical wall. It is not a shell or a boundary that you can touch. It is a limit built into space-time itself. Once something crosses this limit, escape is no longer possible. The event horizon is defined by one simple idea. The escape speed becomes equal to the speed of light. Escape speed is the speed you must reach to break free from gravity. For Earth, it is about 11 kilometers per second. For the Sun, it is much higher. But for a black hole, the escape speed reaches the speed of light. Since nothing in the universe can go faster than light, nothing that crosses the horizon can come back out. Not matter, not light, not even information in the way we normally understand it. This makes the event horizon a unique place. Outside it, physics behaves normally. Light can move freely. Time flows in a familiar way. Gravity is strong but manageable. But as you approach the horizon, everything begins to change. Space curves deeply. Light bends inward. Time slows. And from the outside, objects appear to freeze at the boundary. Imagine watching someone fall toward a black hole. As they approach the event horizon, their motions slow. Their voice becomes deeper. Their signals stretch into longer wavelengths. Their light shifts from visible to red. At the horizon, they appear to stop completely. Their image fades until it disappears. From your point of view, they never cross the event horizon. They simply freeze and fade. But from their point of view, nothing strange happens at the boundary. They fall, they drift, they cross the horizon silently. There is no barrier, no line on the ground, no sudden jolt, nothing to warn them that they have reached a point of no return. This is one of the strangest facts about event horizons. They are visible only from a distance. For the falling object, the horizon does not exist. Two realities coexist at once. To an outside observer, time stops at the horizon. To a falling observer, time continues normally. This is not a trick of perception. It is a real difference in the way time flows near extreme gravity. Now imagine the structure of space near the event horizon. Far from the black hole, space is nearly flat. Light moves in straight paths, clocks tick at their usual rate. But closer to the horizon, space is curved inward. Light bends sharply. Clocks tick more slowly. The flow of time becomes distorted. If you sent a beam of light outward from just above the event horizon, the beam would struggle. It would lose energy as it climbed out of the gravitational field. It would stretch into longer wavelengths. A photon emitted red would reach distant observers as infrared or radio. From just below the horizon, the photon would not escape at all. Light is trapped not because the black hole pulls it back, but because space-time itself funnels every path inward. Inside the horizon, all possible paths lead toward the singularity. Outside the horizon, some paths lead outward. At the horizon, no outward path remains. This is why the event horizon marks the end of escape. Now think about something falling in: a rock, a spacecraft, a star, a cloud of gas. As it approaches the horizon, tidal forces grow stronger. The object feels a difference in gravity between the parts closer to the black hole and the parts farther away. This difference stretches the object. The stretching increases until the object becomes a long, thin filament. This is spaghettification, gravity pulling harder on one end than the other. For small black holes, tidal forces near the horizon are extreme and deadly. For supermassive black holes, the horizon is so large that stretching is gentle at first. You could drift through without noticing. The danger appears later, deeper inside. Now consider the information carried by the falling object. In ordinary physics, information about matter, its structure, its properties, its arrangement, should never be lost. But black holes seem to destroy information. Anything that crosses the horizon disappears from the universe. This idea bothered physicists for decades. Stephen Hawking's work showed that black holes can slowly evaporate by emitting radiation. But if a black hole evaporates completely, what happens to the information that fell inside? Does the universe forget? This question forms the core of the information paradox, a problem so deep that it forces gravity and quantum mechanics into conflict. The paradox belongs to later parts of this series, but it begins here at the event horizon. Because the horizon is not just a surface of no escape, it is a surface where our understanding of the universe breaks. Now think about the horizon from another angle. To an outside observer, the event horizon is a frozen boundary. Objects seem to approach it infinitely slowly. They fade but never cross. This creates an image of a black hole that is almost solid. The horizon looks like a surface made of suspended matter, but this is only an illusion from the outside view. The matter falls in, but the last light it emits takes longer and longer to reach us, stretching until it becomes invisible. To the falling object, there is no frozen layer. To the universe, the frozen layer appears real. Both perspectives must be reconciled. Now consider time more deeply. Time is not the same for every observer. Near strong gravity, time slows. At the horizon, for an external observer, time nearly stops. This raises a strange question. What is it like inside a region where time barely moves from the outside view? How does an object experience time after crossing? The answer is simple. It experiences time normally until it reaches the singularity. The outside view and the falling view cannot be compared directly. They are two valid descriptions of spacetime from two different vantage points, and this is part of the mystery. Now think about the sheer simplicity of the event horizon. It is defined by one number, the black hole's mass. Add more mass, and the horizon grows. Remove mass, and it shrinks. If the black hole spins, the horizon becomes oblate, flattened at the poles. If the black hole carries electric charge, the horizon shifts in shape. But the concept remains the same. The horizon is the surface where escape ends. The horizon is the last boundary where the universe as we know it still operates. Inside, gravity grows stronger than any known force. Inside, space curves sharply inward. Inside, the rules of relativity dominate completely. Inside, the flow of time becomes unpredictable. And further inside lies the singularity, the place where curvature becomes infinite. Now consider the emotional weight of this. A star collapses. It dies. It leaves behind a region of space where no message can escape. No light can return. No information can be retrieved. The star once gave off light across space. Now it is a dark region that hides everything that happens within. The event horizon is the curtain that hides the universe's deepest. secrets. Everything beyond this boundary becomes invisible forever. It does not matter how powerful your telescope is. It does not matter how advanced your technology becomes. The horizon is a perfect hiding place. We cannot look inside a black hole. We cannot send signals through it. We cannot retrieve anything that enters it. The event horizon is the universe's way of saying, you cannot know what happens next. And that is why black holes fascinate us. They are not only extreme objects of gravity, they are limits to knowledge. They are boundaries of physics. They are doors that open only one way. Everything we know about the universe stops at the horizon. Everything beyond it belongs to the unknown. And no matter how advanced science becomes, there may always be things that remain hidden behind that boundary. But the story does not end at the horizon. To understand black holes completely, we must now go deeper. We must examine what actually happens to matter and space once the horizon is crossed. We must examine the stretching of space-time. We must examine the fall into darkness. That is where the next part begins. A black hole becomes truly strange only when you begin to imagine what happens to something that falls inside it. The event horizon is the line where escape ends, but the fall toward the singularity is where reality itself changes shape. This fall is not just a plunge downward, it is a journey into a place where space stretches, time distorts, and the rules of physics lose their familiar meaning. The most famous idea associated with falling into a black hole is spaghettification. The name sounds playful, but the physics behind it is anything but gentle. Spaghettification happens because gravity is not uniform across your body. If your feet are closer to the black hole than your head, the gravity at your feet is stronger. This difference stretches your body along the direction of the fall. At first, the stretch is small, then it grows, then it becomes extreme. In small black holes, this stretching becomes lethal long before you reach the event horizon. Tidal forces grow violently as you approach. Your body is pulled apart. Atoms separate, molecules tear, even particles may be stretched along curved paths. The black hole does not crush you instantly. It pulls you apart piece by piece, but supermassive black holes behave differently. Their event horizons are so large that the gradient of gravity at the horizon is gentle. You could cross the horizon without feeling anything. There is no sudden force, no violent shift, no tearing at the boundary. You drift inside without realizing you have crossed the point of no return. You would still feel normal. Space around you would still look ordinary. Even the stars above might still be visible. The danger grows only as you move inward. Inside the horizon, the curvature of space-time changes direction. Outside, time moves forward, and space can be travelled freely. Inside, time points inward. No matter what direction you try to move, your path curves toward the singularity. It is not gravity pulling you. It is space-time funneling you to the centre. Moving forward in time means moving deeper into the black hole. This is one of the most difficult ideas to accept. Inside a black hole, going inward is not a choice. It is the only possible direction. You cannot stop. You cannot hover. You cannot reverse course. No engine can help you. Even light cannot escape. You are carried inward, not because of force, but because of geometry. Now imagine the view as you fall. The universe behind you appears to speed up. Light from the outside world, blue shifts. You see distant stars racing through their life cycles in seconds. Galaxies rotate rapidly. Time outside seems to accelerate in ways that make no sense. Meanwhile, your own time feels normal. Your heartbeat, your thoughts, your movements, everything continues smoothly. This difference in time is not an illusion. It is real. Extreme gravity warps time so dramatically that two observers can experience completely different timelines. 1 second for you might be millions of years for the outside universe. This brings us to one of the strangest consequences of falling into a black hole. You could witness the far future of the universe as you fall. Stars being born, galaxies merging, clusters drifting apart, all compressed into a brief visual explosion. The universe ages rapidly for everyone else, while your own time remains slow. But the visuals do not last. As you fall deeper, light from the outside world bends around you. The outside universe shrinks into a small bright circle above you. Everything else becomes dark. The black region grows. The visible universe collapses into a tiny spot. This is not because the outside world is disappearing. It is because space-time itself is curving in a way that funnels all incoming light into one direction. Then the circle of light fades. Darkness surrounds you completely. Now the only thing ahead is the singularity. No force can stop you from reaching it. You cannot orbit it. You cannot avoid it. You cannot drift around it. Inside the horizon, the singularity is not a point in space. It is a moment in time. You reach it the same way you reach the future, by moving forward. And since time cannot be stopped, the singularity cannot be avoided. Now think about what the singularity is. In simple terms, it is the end of the laws of physics as we know them. Space and time reach infinite curvature. Density becomes infinite. The equations of general relativity break. Our understanding ends. The singularity is not a physical object. It is a mathematical description of where our theories fail. Relativity says space-time curves infinitely. Quantum mechanics says infinity is impossible. Both cannot be true. Something deeper is missing. The fall into the singularity is not just the end of a physical journey. It is the place where science itself must eventually evolve. Black holes force us to admit that our theories are incomplete. They point to a new kind of physics, a unified theory that merges gravity and quantum mechanics into one framework. But until that theory exists, the singularity remains a mystery. A region hidden behind the horizon, unreachable, unobservable, untouchable. Every object that falls in carries information about itself, mass, charge, spin, yet the details vanish, at least according to classical physics. Quantum physics says information must survive. Relativity says the singularity erases it. Hawking radiation complicates everything further. This is why black holes are not just astronomical objects. They are puzzles, they are contradictions waiting to be resolved. Now return to the falling object one more time. The object stretches, it speeds up, it drifts deeper, it moves toward the singularity. But at no point does it feel the boundary of the event horizon. The horizon is not a wall. It is a limit from the outside, not from the inside. The fall ends at the singularity, where time itself ends. This is the true definition of the singularity, a place where the future stops existing. No path leads beyond it. No continuation of time is possible. The end of the fall is the end of the journey. Now step back and think about what this means for black holes as a whole. They are regions of space where time and space exchange roles. They are funnels that redirect all motion inward. They are one-way doors in space-time. They are boundaries where the universe hides information. Black holes show us that physics, as powerful as it is not finished. Our equations explain everything up to the horizon. They describe the curvature of space, the flow of time, the behavior of matter. But inside the horizon, and especially at the singularity, our equations fail. Something more fundamental must exist. The fall into a black hole is not just a physical descent, it is a descent into the unknown. It reveals how much of the universe we do not understand. Black holes are not the end of science, they are the beginning of deeper science. They point toward new laws, new ideas, new forms of understanding. They show us the cracks in our theories and guide us toward a future where gravity and quantum mechanics will finally speak the same language. But before we reach that future, we must understand the different kinds of black holes that exist in the universe. Not all black holes behave the same way. Some are tiny and violent, some are enormous and calm, some spin rapidly, some power jets that stretch across galaxies, some are quiet giants sitting in darkness. Each type teaches us something different about the universe. That is where the next part takes us. A black hole becomes truly mysterious only once you ask what happens inside it. Outside the event horizon, Einstein's equations describe everything with precision. Space curves, time slows, light bends, matter heats. All of this is understandable. Strange, yes. Extreme, yes. But still part of known physics. Inside the event horizon, something different happens. The familiar structure of spacetime collapses. The laws we rely on break apart. Predictions become impossible. The universe stops making sense in the way we expect. Inside is not just darkness. It is a place where physics loses its foundation. The core of this mystery is the singularity. A singularity is the point where the curvature of spacetime becomes infinite. Density becomes infinite. Forces become infinite. The equations of general relativity stop working because they produce infinities that have no physical meaning. Infinity in mathematics is useful. Infinity in physics is a sign of something missing. The singularity is not a physical object. It is not a point in space that you can approach like a mountain peak. It is a breakdown in the rules we use to describe space. It marks the edge of our knowledge. Everything we call physics stops working the moment you try to describe the singularity in detail. To understand why, imagine compressing matter. Compress it enough, and electrons are forced into protons, making neutrons. Compress it further, and neutron matter becomes so dense it forms a neutron star. Compress it beyond that, and even neutrons cannot resist collapse. Gravity wins completely. There is no pressure strong enough to push back, no particle strong enough to resist, no structure stable enough to remain intact. Gravity crushes everything. Relativity describes this collapse perfectly, but only up to a point. It predicts that gravity will compress matter into a region of zero volume and infinite density. But quantum mechanics, the theory of the very small, does not allow infinities like this. Quantum forces should resist collapse in some way. Yet relativity ignores quantum effects entirely. These two theories, quantum mechanics and general relativity, do not agree inside a black hole. This is the heart of the problem. Einstein's theory breaks at the singularity. Quantum physics breaks at extreme gravity. Neither theory can describe what truly happens inside. This is why black holes reveal the need for a deeper theory, a theory of quantum gravity that unites the two sets of laws. Without it, the singularity remains an unsolved puzzle. Now consider what it actually feels like to fall toward this region. Inside the event horizon, time becomes warped, space becomes warped. The familiar separation between space and time begins to dissolve. The direction of your fall becomes the flow of time itself. Moving forward in time means moving toward the singularity. You are carried inward by the structure of space-time. No force can stop your descent. The singularity is not just a place in space, it is your unavoidable future. Now think about this carefully. When you fall inside, the singularity lies ahead not because you're being sucked toward it, but because it is the moment your timeline ends. You do not fall into it the same way you fall into a pit. You fall into it the same way you reach tomorrow. This is one of the strangest consequences of relativity. Inside a black hole, time itself brings you to the singularity. It is not a place you can avoid because you cannot avoid the future. Now consider what happens to matter as it approaches the singularity. Outside, matter forms an accretion disk. It heats, it radiates, it tears apart. But once inside the event horizon, there is no outward release. No heat escapes, no light escapes, no information escapes. Everything falls inward. Everything is compressed. As matter piles up, the curvature increases. The density increases. The gravity increases. New layers fall in and join the collapse. The interior of a black hole is not empty. It contains the history of everything that has ever crossed its horizon. Compressed, shredded, lost to the outside universe, inside, matter becomes unrecognizable. The concept of shape stops mattering. The concept of volume stops mattering. The concept of distance stops mattering. All paths curve toward the singularity. Now think about the information carried by matter. Every atom has a structure. Every particle has properties. Every arrangement contains information. According to quantum mechanics, information can never truly be destroyed. According to relativity, everything that falls into a black hole is erased at the singularity. These two ideas cannot both be right. This is the information paradox, one of the greatest conflicts in theoretical physics. If black holes destroy information, then the basic framework of quantum mechanics breaks. If information survives, then general relativity fails. No theory fully explains how information behaves inside a black hole. Some theories propose that information is stored on the event horizon itself, like a hologram. Others suggest that information escapes slowly through Hawking radiation. Some propose that the singularity is not really a point but a finite region where quantum effects dominate. Some suggest that the inside of a black hole connects to another region of spacetime, like a wormhole. Some propose that the singularity is replaced by a bounce into a new universe. None of these ideas are proven. All of them attempt to solve a problem we cannot observe directly. The interior of a black hole remains hidden forever. Now consider the concept of space inside the horizon. Outside space is a place you can move through. Inside, space becomes time-like. Your choices shrink. You lose the freedom to move outward. You can only move inward in the same way you can only move forward in time. This raises a strange question. What does space mean when space forces you in one direction? What does time mean when time stops flowing normally? These questions show that our basic assumptions about reality do not apply inside a black hole. Even the simplest ideas, before, after, here, there, lose their meaning. Now think about the singularity again. In classical theory, everything ends there. Not just matter, but space-time itself. There is no beyond the singularity. There is nothing to describe, no future, no continuation. The timeline ends, the fall stops, but quantum physicists believe there must be something deeper. They believe that our current laws simply lack the tools to describe what happens at extreme densities. Just as Newton's gravity was replaced by Einstein's relativity, relativity may be replaced by a more complete theory, one that explains what happens at the smallest scales and highest energies. Black holes force this shift. They highlight the places where our understanding breaks. They expose the boundaries of our knowledge. This is why black holes are not just astronomical objects. They are testing grounds for the deepest laws of nature. Now think about the emotional weight of this. The universe contains regions where all known laws collapse, places where knowledge ends, places where no observer can report back, places where reality becomes unrecognizable. And yet these places are common. Millions of black holes drift quietly in our galaxy. Each one contains a singularity, a region where the universe hides its secrets behind an event horizon that no signal can cross. Every black hole is a doorway into unknown physics. They are not exceptions. They are features of the universe. They are clues. They suggest that something enormous is missing from our understanding, something beyond relativity, something beyond quantum mechanics, something that combines both into one framework. Inside the singularity may lie the blueprint of the universe, the foundation of spacetime, the true nature of matter and energy, the reason gravity behaves the way it does. We do not know. We cannot know, not yet, but black holes guide us toward these answers. Now that we have explored the collapse of physics inside a black hole, the next step is to understand black holes in their largest form. Not the small ones created by dying stars, but the enormous supermassive black holes that sit at the centers of galaxies and control the structure of the cosmos. These giants behave differently. They grow differently. They shape the universe differently. And that is where the next part takes us. Black holes come in many sizes, but the most important ones in the universe are the supermassive black holes. These giants sit at the centers of galaxies, including our own Milky Way. They contain millions, sometimes billions, of times the mass of the Sun. They are the heaviest objects known, and their influence extends far beyond the region where their gravity dominates. They shape galaxies, control star formation, affect cosmic evolution, and act as anchors around which entire galaxies rotate. A supermassive black hole is very different from a black hole made by a dying star. A stellar mass black hole might be a few kilometers wide. A supermassive black hole can be as large as the orbit of a planet. The one at the center of the Milky Way, Sagittarius A8, has a mass of about 4 million suns. The black hole at the center of the galaxy M87 has a mass of around 6.5 billion suns. These objects contain enough mass to hold entire regions of space together. One of the surprising facts about supermassive black holes is that they do not tear apart everything around them. If our Sun were replaced with a black hole of the same mass, Earth's orbit would not change. It would become dark, but the orbit would remain stable. Supermassive black holes follow the same rules. Stars orbit them, just as planets orbit stars. The difference is scale. A supermassive black hole sits at the center of a galaxy and influences hundreds of billions of stars. Now consider how these giants form. Their origin is still a mystery. They may begin as the collapse of enormous gas clouds in the early universe. They may grow from the merging of many smaller black holes. They may come from the rapid collapse of the first supermassive stars. Whatever the origin, once they appear, they grow quickly. They feed on gas, stars, and even other black holes. They attract matter across vast distances. A supermassive black hole that is actively feeding can become brighter than its entire galaxy. As matter spirals into the black hole, it forms a hot accretion disk. The temperature becomes so high that the disk shines across the electromagnetic spectrum. Jets shoot out from the poles at nearly the speed of light. These jets can extend for thousands or millions of light years. They heat gas, prevent galaxies from forming too many stars, and shape entire galactic structures. A quiet black hole is invisible. A feeding black hole is one of the brightest objects in the universe. This contrast shows the complexity of black holes. They are both destroyers and engines of creation. When they feed, they return energy to the galaxy. When they are quiet, they simply act as massive anchors. Now think about the role of supermassive black holes in galaxy formation. Every large galaxy we know has a central black hole. The mass of the black hole correlates with the mass of the galaxy around it. The bigger the galaxy, the heavier the black hole. This suggests that galaxies and their central black holes grow together. A galaxy is not just a collection of stars, it is a structure shaped by the gravitational and energetic influence of its central black hole. In the Milky Way, Sagittarius A sits quietly. It does not feed heavily, only small amounts of gas and dust fall toward it. But we know it was more active in the past. Radiation marks on nearby clouds show that our black hole flared thousands of years ago. It may flare again in the future if a large cloud or a star drifts too close. Now imagine the centre of the Milky Way. Stars crowd tightly in the region around Sagittarius ATI. They orbit at tremendous speeds. Some move so fast that only the gravity of a black hole could keep them in their paths. These stars, called S-stars, provide direct evidence for the existence of the black hole. Scientists have tracked their orbits for decades. The only explanation for their motion is an extremely massive object, no larger than our solar system. This is how we know the Milky Way's black hole is real. We see stars orbiting something invisible. We measure their speed. We calculate the mass. The result is clear: a supermassive black hole. Now consider the galaxy M87. Its central black hole was the first ever photographed. The black circular shadow in the famous image is not the black hole itself. It is the shadow cast by the event horizon. The glowing ring around it is the heated gas spiraling inward. This image showed that supermassive black holes are not ideas. They are physical objects that can be observed, measured, and studied. Supermassive black holes shape galaxy evolution in several ways. When they feed, they blow winds of radiation and jets through the galaxy. These winds heat surrounding gas. If the gas becomes too hot, it cannot collapse into new stars. This slows star formation. A galaxy with an active black hole can become quiet or quenched. Star formation may drop dramatically. Galaxies with quiet black holes often have fewer young stars. This means a black hole can control the growth of its entire galaxy. At first, this seems strange. A region, only a small part of the galaxy's size, can influence billions of stars. But this is how feedback works. The black hole does not act through gravity alone. It acts through energy. A feeding black hole releases more energy than the combined output of all the stars around it. This energy heats gas across enormous distances. It shapes the evolution of the galaxy. Without this mechanism, galaxies would likely form too many stars too quickly and collapse their gas supplies. Black holes regulate this process. Now think about the universe as a whole. Without supermassive black holes, galaxies would not look the way they do. The cosmic web would be different. Star formation history would change. The distribution of matter would shift. Black holes play a role far beyond what their size might suggest. Now consider the emotional side of this. At the centre of the galaxy you call home sits a silent giant. It has no light, it has no surface, it has no sound, it simply is. It influences stars across thousands of light years. It anchors the Milky Way, yet it remains completely invisible. If you visited the centre of the galaxy, you would not see it. You would see stars, gas clouds, dust lanes, but not the black hole itself. And still, everything revolves around it. This is the kind of structure the universe prefers: massive, silent, invisible, powerful. The Milky Way is not special. Every major galaxy has a similar giant. These black holes are the engines of galactic evolution. They influence the universe at scales far larger than their horizons. They show that size does not always determine importance. A black hole smaller than a solar system can influence a galaxy larger than light years. Now think about what happens when supermassive black holes merge. When galaxies collide, their central black holes spiral inward. They orbit each other for millions of years. They emit gravitational waves. Finally, they merge into a larger black hole. This process releases enormous amounts of energy and sends ripples through space-time. This leads to the next major topic in the series, gravitational waves, and how black holes change the structure of space-time when they collide. That is where the next part takes us. Black holes do not remain alone forever. The universe is built on collisions and mergers. Stars collide, galaxies collide, and when galaxies collide, their central black holes are drawn toward one another. Over millions of years, these giants spiral inward, lose energy, and eventually merge. When they merge, the event is not quiet. It is not gentle. It is not invisible. It produces ripples in space-time itself. Gravitational waves. Gravitational waves are one of the most important discoveries in modern physics. They are not vibrations in air. They are not waves of sound. They are waves in the fabric of space-time. To understand why black hole mergers create these waves, imagine space-time as a flexible sheet. Place two heavy balls on it. The sheet curves. If the balls move around each other, the sheet ripples. These ripples spread outward at the speed of light. Now replace the balls with two black holes. Replace the sheet with space-time. The result is the same idea, but on a cosmic scale. The motion of the black holes disturbs space-time, sending waves outward across the universe. When those waves reach Earth, they stretch and compress everything. Atoms, buildings, planets, but only by distances smaller than the width of a proton. Measuring these tiny distortions seemed impossible for decades. But in 2015, the LIGO detectors made the first direct observation of gravitational waves. Two black holes, each about 30 times the mass of the Sun, had merged over 1 billion light-years away. Their collision released more energy in a fraction of a second than all the stars in the universe combined. Most of that energy did not appear as light. It appeared as gravitational waves. This event changed science forever. It confirmed a major prediction of Einstein's theory of general relativity. It opened a new way of observing the universe. For the first time, we could listen to cosmic events that light could not reveal. Black hole mergers do not produce light because black holes absorb everything around them. But gravitational waves pass through everything. They do not scatter. They do not dim. They do not get absorbed by gas or dust. They carry information directly from the most extreme regions of space-time. This makes them a perfect tool for studying black holes. Now think about how two black holes merge. At first, the black holes orbit each other slowly. They may orbit for millions or billions of years, but as they orbit, they emit gravitational waves. Emitting waves carries energy away from the system. Losing energy causes the black holes to spiral inward. Their orbit shrinks, their speed increases, the waves become stronger. Eventually, the black holes move close enough that their event horizons begin to interact. They circle each other at a significant fraction of the speed of light. Their horizons distort. Space stretches and twists. Time behaves unpredictably. The curvature becomes extreme. Finally, the two black holes merge into a single, larger black hole. The merge produces a last burst of gravitational waves, the loudest moment in space-time. Then everything quiets. The new black hole settles. Its horizon becomes smooth. Its shape stabilizes. This settling phase also produces gravitational waves. These waves are like the ringing of a bell after it has been struck. Physicists call this the ring-down phase. The tone of these waves reveals the properties of the final black hole: its mass, its spin, its shape. Every black hole has a unique gravitational voice. Now consider the importance of these mergers. Black hole mergers grow black holes. They take medium-sized black holes and create larger ones. Over billions of years, mergers may help form the supermassive black holes at the centers of galaxies. If smaller black holes merge repeatedly, the mass increases step by step. The universe may have used this method to build the enormous black holes that appeared early in cosmic history. Black hole mergers also help us understand spacetime. The waves they produce reveal how gravity behaves in extreme environments. They test Einstein's theory in ways that no other experiment can. Every merger is a natural laboratory, showing how spacetime curves when pushed to its limit. Now think about where these mergers happen. Some occur when two massive stars in a binary system evolve together. Each star collapses into a black hole. The black holes remain gravitationally bound. Over time, they spiral inward and merge. Other mergers occur in dense star clusters, where black holes collide randomly. The largest mergers happen when galaxies merge. In large galaxies, the central supermassive black holes eventually find each other and begin their slow dance toward collision. These supermassive mergers release gravitational waves far larger than anything LIGO can detect. They're so powerful that they create waves stretching across entire galaxies. Detecting them requires different tools: pulsar timing arrays that measure delays in the signals from distant neutron stars. Early evidence suggests these cosmic-scale waves may already have been detected. Now think about what a merger means for the galaxy. When two supermassive black holes approach, they disturb the stars around them. Some stars are flung out of the galaxy entirely. Others fall inward and feed one of the black holes. Gas heats up. Jets form. The center of the galaxy becomes chaotic. After the merge, the new black hole may recoil from the center, kicked by the uneven emission of gravitational waves. In extreme cases, the merged black hole could be kicked out of the galaxy completely, drifting through intergalactic space. This possibility is astonishing. A black hole billions of times the mass of the Sun drifting alone between galaxies. No stars, no gas, no light, just a silent giant moving through darkness. Black hole mergers reveal that the universe is not static. It is dynamic. It evolves. It changes shape. It creates new structures. It destroys old ones. Galaxies merge, collide, scatter, and reshape themselves. Black holes grow through these events. They are not passive. They are active participants in cosmic evolution. Now consider the emotional dimension. Two stars lived billions of years. They died. They collapsed into black holes. They drifted through space. They eventually met, and in a single moment, their entire histories ended in silence, but not without a trace. The trace is the ripple in space-time. A ripple that spreads across the universe. A ripple that eventually reaches Earth. A ripple that tells us a story from 1 billion years ago. This is the power of gravitational waves. They let us observe the universe without light. They let us detect events we could never see. They let us study black holes directly. They open a new window into the cosmos. Now that we understand how black holes merge and send messages across space-time, we can address one of the deepest mysteries in physics. What happens to information that falls into a black hole? This question leads to the next major chapter. Black holes challenge science in many ways, but the information paradox is the deepest and most troubling problem they create. It is not about gravity. It is not about collapse. It is not about event horizons or spaghettification. It is about something more fundamental, whether the universe preserves information. This question sounds abstract, but it lies at the heart of physics. Every law we know depends on it. In physics, information is not the same as data on a computer. Information is the basic structure of matter. How particles are arranged, how atoms interact, how quantum states evolve. According to quantum mechanics, this information is never lost. It can change forms, it can spread, it can become unrecognizable, but it cannot disappear. The universe does not delete history. Black holes appear to break this rule. Imagine a star that collapses into a black hole. Before collapse, the star had structure. It had temperature, magnetic fields, chemical composition, patterns in its interior. All of that is information. After collapse, the black hole only retains three things: mass, spin, and electric charge. Everything else vanishes. The details of the star's interior are gone. Every particle that falls in also loses its identity. This is the problem. Relativity says information falls into the singularity and disappears forever. Quantum mechanics says information can never be destroyed. Both theories are extremely successful. Both describe the universe with remarkable accuracy. But inside a black hole, they disagree. This disagreement is not a small technical issue. It is a direct conflict between the two pillars of modern physics. This is the information paradox. Stephen Hawking made this problem much worse in the 1970s, when he discovered that black holes emit radiation. Before Hawking, black holes were considered eternal. Once matter fell in, it stayed there. But Hawking showed that quantum effects near the event horizon cause black holes to slowly release energy. This emission is called Hawking radiation. Hawking radiation does not come from inside the black hole. It comes from quantum fluctuations just outside the horizon. Particles and antiparticles constantly pop in and out of existence in empty space. Near the event horizon, one particle may fall in while the other escapes. The escaping particle becomes Hawking radiation. Over trillions of years, this process causes black holes to shrink and eventually evaporate completely. This creates a new problem. If a black hole evaporates entirely, what happens to all the information inside it? Does it vanish with the black hole? Does the universe truly lose memory of everything that fell in? Hawking's original conclusion was yes. Information is lost. Most physicists believed this could not be right because it violates quantum mechanics at a deep level. If information can be lost, then quantum mechanics collapses. Predictability collapses. The mathematical foundation of physics collapses. The paradox forced scientists to rethink everything about black holes. Now consider the three main possibilities physicists have explored. 1. Information escapes through Hawking radiation. This idea suggests that the radiation somehow carries subtle quantum information, not in an obvious way, but encoded in complex correlations. At first, Hawking rejected this, but later he accepted it might be true. If the radiation encodes information, then the black hole leaves behind a record of everything that fell into it. This would preserve quantum mechanics, but it requires a mechanism we do not yet understand. 2. Information is stored on the event horizon. This idea comes from the holographic principle. The principle says that all the information inside a region of space can be stored on its boundary, like a hologram. In this view, the event horizon becomes a kind of storage surface. Anything that falls in leaves its information on the horizon. The black hole's surface area, not its volume, determines how much information it can store. This idea is elegant. It connects black holes to deeper theories about spacetime. It suggests that the universe might itself be holographic in some way, but it raises new questions. How is the information stored? How is it released when the black hole evaporates? Is space-time fundamentally two-dimensional at its deepest level? 3. Black holes do not fully evaporate. This idea proposes that after evaporation, a small remnant remains, a stable particle-like object that stores the information. This avoids destroying information. But these remnants would need to store enormous amounts of data in a tiny space. It is unclear whether this is possible. Now consider the human side of this paradox. Scientists spent decades fighting over it. Arguments filled conferences. Papers challenged each other. Whole careers focused on solving the missing information. This paradox is not simply a theoretical puzzle. It is a clue that something deep is missing from our understanding of the universe. It tells us that general relativity, though brilliant, is incomplete. It tells us that quantum mechanics, though powerful, cannot explain everything. It points to a new theory, a unified framework that merges the two. This is why black holes matter. They force physics to evolve. Now think about what this paradox reveals about the nature of space-time. If information cannot be destroyed, then space-time must behave differently near the horizon than we currently believe. Maybe the horizon is not a simple one-way surface. Maybe space-time is woven in a way that preserves information in hidden structures. Maybe quantum entanglement creates connections that reappear in Hawking radiation. Some theories propose that the inside of a black hole is connected to the outside through quantum bridges called Einstein-Rosen bridges, or wormholes. Others propose the firewall hypothesis, which suggests that the horizon becomes a violent region that burns information instead of hiding it. This would mean falling into a black hole is not smooth. It would mean relativity breaks at the horizon. Every theory solves one problem, but creates another. That is the nature of the information paradox. Now step back and consider what this means for the universe. Black holes are not simply cosmic vacuum cleaners. They are not simply dead stars. They are not simply regions of strong gravity. They are laboratories. They are clues to the true nature of reality. They are signs that space-time is built from something deeper than geometry. Black holes reveal the cracks in our theories. They highlight the limits of what we know. They show us that the universe is more complex than the equations we currently use. Understanding black holes will require a new kind of physics, a theory that merges relativity and quantum mechanics into one complete framework. Some call it quantum gravity, some call it string theory, some call it loop quantum gravity. Others believe the answer has not been discovered yet. Whatever the final theory looks like, black holes will be at the center of it. Now that we have explored the paradox, the next step is to understand what black holes teach us about the universe. They are not isolated curiosities. They influence galaxies, star formation, cosmic evolution, and perhaps even the structure of space-time itself. That is where the next part takes us. Black holes are more than extreme objects. They are windows into the structure of the universe. Every time we study them, we learn something new about gravity, space-time, matter, and cosmic evolution. Black holes are not isolated features scattered randomly through the cosmos. They participate in its structure. They influence galaxy formation. They shape the distribution of matter. They reveal the limits of physical laws. In many ways, understanding black holes means understanding the universe itself. Begin with the most surprising truth. Black holes are simple, but the universe around them becomes more understandable because of this simplicity. A black hole erases complexity. It reduces matter to mass, spin, and charge. Because of this, black holes become perfect test objects for studying gravity. They have no internal structure that complicates calculations. They are clean, pure solutions to Einstein's equations. When we study how stars orbit a black hole, how light bends around it, and how time behaves near it, we test general relativity at its strongest. Black holes show us exactly how space-time curves. They show us where relativity works flawlessly and where it fails. Every observation of a black hole pushes the boundaries of physics. When we watched stars orbit the black hole at the center of the Milky Way, we confirmed Einstein's predictions. When we recorded gravitational waves from merging black holes, we confirmed relativistic dynamics. When we photographed the shadow of a black hole, we confirmed the bending of light around curved spacetime. Black holes consistently match the predictions of relativity up to a point. That point is the singularity. The singularity is the region relativity cannot describe. And that failure gives us a clue. Relativity is incomplete. The laws of physics work beautifully for planets, stars, and galaxies. But black holes reveal where those laws must eventually be replaced by a deeper theory. Now consider the role of black holes in shaping galaxies. When a black hole feeds, it releases enormous amounts of energy. This energy heats gas, prevents clouds from collapsing, and controls the rate of star formation. A galaxy is not free to grow without limits. Its central black hole acts as a regulator. Too much star formation, the black hole sends energy outward and slows the process. This balance is important. Without it, galaxies would burn through their gas too quickly, star formation would peak early, and galaxies would die young. The universe would not look the way it does today. Supermassive black holes help galaxies live longer, more regulated lives. They preserve gas, they control structure, they influence the movement of stars, they stabilize the centers of galactic systems. The deeper you look into galactic evolution, the more black holes appear as quiet architects. They do not just sit at the center, they participate, they guide, they shape. Now think about the early universe. The first black holes formed within a few 100 million years after the Big Bang. Some of them grew into giants, millions or billions of solar masses, faster than we expected. Their rapid growth tells us something important. Matter in the early universe was dense, turbulent, and ready to collapse. Supermassive black holes may have formed directly from collapsing gas clouds rather than smaller stars. They may have been born big. This would explain why many early galaxies already had massive black holes at their centers. When we observe distant quasars, we're looking at the early universe. These quasars shine brightly because their black holes are feeding rapidly. The light from those feeding disks traveled billions of years to reach us. They show us how the universe looked when it was young. They show us the role black holes played in the first galaxies. Black holes are not signs of destruction. They are signs of structure forming. Now think about the cosmic web, the enormous network of galaxies stretching across the universe. Black holes help shape this structure indirectly by regulating galaxy formation. Galaxies gather into clusters. Clusters gather into superclusters. Dark matter forms the backbone of this cosmic web. But black holes influence how galaxies grow along this web. Now consider another profound insight. Black holes reveal that space-time is dynamic. It bends, it stretches, it ripples, it evolves. When black holes merge, space-time rings like a struck bell. When a black hole spins, space-time twists around it. When a black hole forms, space-time collapses inward. This tells us that space-time is not a passive background. It is active. It participates in physical processes. This is one of the most important ideas in modern physics. Gravity is not a force pulling objects together. Gravity is the shape and motion of space-time. black holes are the purest expression of this idea. They show us curved space-time at its strongest. Now think about the event horizon again. It is not a surface you can touch. It is a mathematical boundary, but it behaves like an object. It grows when the black hole absorbs matter. It shrinks through Hawking radiation. It can vibrate during mergers. It has temperature. It has entropy. It behaves as if it is made of microscopic pieces, but we do not know what those pieces are. This connection between black holes and thermodynamics is one of the deepest discoveries in physics. It suggests that space-time may have an atomic structure. Just as matter is made of molecules and atoms, space-time may be made of smaller components. Black holes hint at this invisible structure. They point to something deeper. Now think about how black holes guide us toward a unified theory. Relativity describes gravity. Quantum mechanics describes particles. The two theories conflict at the singularity. The event horizon hints at a deeper connection between information and gravity. Hawking radiation connects black holes to quantum fields. Every part of a black hole touches every part of physics. This is why they are so important. Now consider the universe's long-term evolution. Black holes will eventually dominate the far future. Stars will die, galaxies will fade, but black holes will persist. They will remain active far longer than any star. They will slowly evaporate over unimaginable timescales. Even after galaxies fade, black holes will continue to influence their surroundings. Their evaporation will be one of the final processes in the universe. Black holes are not temporary features. They are cosmic survivors. But the most important thing black holes reveal is something more philosophical. The universe hides its deepest truths at its most extreme edges. Where gravity is strongest, our theories fail. Where space-time curves most violently, our equations collapse. Where the event horizon forms, information behaves strangely. Black holes show us how much we still do not understand. They highlight the gap between our theories and reality. They remind us that the universe is larger, stranger, and more complex than our current knowledge. They are not the end of understanding. They are the beginning of deeper understanding. Now that we know how black holes inform our understanding of physics and the universe, we must look forward into the deep future of black holes. What will they become? How long will they survive? What happens when the universe becomes cold and dark? That is the final step in this journey. Black holes are often imagined as the ultimate destroyers, but that is not their final identity. They are long-term survivors in a universe that constantly changes. Stars die, galaxies merge, gas clouds disperse, but black holes continue to exist through almost every cosmic era. To understand the future of the universe, you must understand the future of black holes. They will remain long after everything else has faded. The universe today is young compared to its final form. There are stars everywhere. Galaxies are bright. Matter is dense enough to form new structures. But all of this will change. Stars will exhaust their fuel. Gas will run out. Galaxies will become quieter. Black holes will become the dominant structures, not because they grow, but because everything else decays. Begin with the next few trillion years. During this time, stars will continue to burn. New stars will form, but star formation will slow. Gas clouds will scatter. As galaxies collide, their central black holes will merge. These mergers will create even larger black holes. Over time, supermassive black holes will become heavier and more numerous. Eventually, the Milky Way will merge with Andromeda. The two central black holes will orbit each other, spiral inward, and merge into a single, giant black hole. This new black hole will contain millions of solar masses. The combined galaxy will become a large elliptical structure. Its star formation will decline. The region will become quieter. This process will repeat across the universe. Galaxies collide. Their black holes merge. The central black holes grow larger. These mergers produce gravitational waves that ripple across cosmic distances. But over time, the universe becomes quieter again. The bright, active era of galaxies gradually fades. Now consider the far future. Long after galaxy collisions slow down, the universe will continue to expand. As expansion accelerates, distant galaxies move away from each other faster than light can travel. Eventually, only the closest galaxies remain visible to one another. The night sky will become darker. The large-scale structure of the universe will become harder to observe. During this era, stars begin to die permanently. Small stars fade into white dwarfs. Large stars explode as supernovae. Neutron stars cool. The universe becomes filled with remnants. The only sources of activity are the black holes consuming what little matter is left. Planets drift in. Stars wander too close. Gas clouds fall inward. But these events become rare. Most of the universe becomes empty. Only black holes remain active. As trillions of years pass, even these events slow. The universe enters what physicists call the degenerate era. It is an era where most matter exists as cold remnants, white dwarfs, neutron stars, and black holes. The temperature of space drops. Energy becomes scarce. The universe becomes quiet. Black holes continue to merge, but these mergers slow down too. The distances between objects grow larger. The universe becomes dominated by dark energy, the mysterious force causing the expansion to accelerate. Black holes drift apart, moving farther from one another as space expands. Now consider what happens when black holes stop feeding. A black hole that no longer gains mass begins to lose mass. Not through collisions, not through interactions, but through Hawking radiation. Hawking radiation causes black holes to evaporate. This process is incredibly slow. For a black hole the mass of the Sun, evaporation takes around 1066 years. For a supermassive black hole, evaporation takes much longer, up to 10 to 100 years. The universe itself is only 10 years old today. Black holes will outlive everything we know by unimaginable orders of magnitude. In the far future, black holes slowly shrink. They emit radiation. Their horizons become smaller. Their temperature increases as they lose mass. As they get smaller, the process accelerates. A black hole's final moments are violent. It releases a burst of energy, then vanishes. Nothing remains. The matter, energy, and information it once held must reappear somehow, according to quantum mechanics. This is one of the reasons physicists believe Hawking radiation must carry information. When the last black hole evaporates, the universe enters its final stage, the heat death or thermal equilibrium era. At this point, the universe becomes a thin, cold sea of particles and low-energy radiation. There are no stars, no planets, no galaxies, no black holes. But this is not the end of physics. It is the beginning of a new set of questions. What does it mean for information to survive without structure? What does it mean for space-time when there are no massive objects left? What does it mean for time when the universe has almost no energy differences? Black holes guide us toward these questions. Now return to the present. Black holes exist across the universe today. They shape galaxies, they merge, they create gravitational waves, they hide information, they reveal the limits of our theories, but they also tell us something important about the long-term fate of reality. Gravity shapes the early universe. Star formation shapes the middle universe. Black holes shape the late universe, Dark energy shapes the final universe. Every era has its rulers. Black holes rule the quiet era that lies ahead. Now consider the emotional scale of this. The universe is vast and indifferent. It evolves without purpose. It expands without pause. It is not fragile in the way living beings are. But inside that vast, indifferent structure, something rare happens. Life appears, awareness appears, meaning appears. Black holes will survive long after life is gone. They will outlive stars, galaxies, and structures of every kind. But they cannot outlive the fundamental questions they create. Black holes remind us that our understanding of reality is temporary. They show us where the universe hides its deepest truths. They lead us to the boundaries of knowledge. They force science to evolve. They do not just collapse matter, they collapse certainty. And in the space where certainty collapses, discovery begins. Now the long story comes full circle. Black holes begin with the death of stars. They grow by shaping galaxies. They challenge physics at the event horizon. They hide mysteries at the singularity. They send messages through gravitational waves. They reveal the connections between information and spacetime. They guide theories of quantum gravity. They dominate the far future of the universe. They evaporate into nothing, and through every stage, they reshape our understanding of reality. Black holes are not endpoints, they are doorways. Doorways into the unknown, doorways into the structure of space-time, doorways into the future of physics, doorways into the ultimate fate of the universe. In the end, black holes do not answer questions, they create them, and that is why they are essential. They keep the search for understanding alive, even in a universe that will one day fall silent. Black holes are the universe's most silent teachers. They bend space, shape galaxies, and push physics to its limits. They remind us how much we still don't understand, and how much more there is left to discover. For now, we stand outside these dark regions, watching from a safe distance, knowing that the deeper we try to look, the more the universe asks new questions. And that is what makes the journey worth continuing.